Welcome to The Explainer. Today, we're jumping into the wild story of chemistry. Think about it. It's a science of creation and destruction, of life-saving medicines and, well, planet-altering pollution. It's this incredible double-edged sword, and we're going to trace its edge all the way from ancient philosophy to the atomic age. So check this out. The same science that powers modern warfare is also the one that feeds the planet. It even created the first synthetic colors. And believe it or not, it all started with something as messy as coal tar. It's an incredible story of transformation. So the big question is, how in the world did we go from just guessing what stuff was made of to actually building our world, atom by atom? I mean, for thousands of years, this was one of the biggest questions we had. What is all this stuff around us, really? And our first shot at an answer, it didn't come from a lab with bubbling beakers. Nope, it came from right inside the human mind, just pure thought. So let's start our story in a world that was run not by experiments, but by big ideas, by philosophy. Okay, so the ancient Greeks, guys like Empedocles, they had this idea that was actually beautifully simple. They thought everything, and I mean everything, was just a mix of four basic things: earth, air, fire, and water. And that idea, it stuck around for over 2,000 years. Now, just look at that compared to what we know today. This huge, sprawling periodic table with over 100 elements. Getting from that simple idea on the left to this incredibly detailed map of reality on the right, well, that's the journey we're on today. But, things started to change. A new way of thinking began to bubble up. People like Jan Baptist van Helmont here started saying, hey, maybe we should stop just arguing and actually look at nature itself for the answers. That simple idea, that shift from argument to observation, it was about to set off a complete revolution. And let me tell you, this wasn't just some small update. This revolution didn't just tweak the old ideas, it totally blew them out of the water. It laid down the fundamental rules of chemistry that we still use today. And things started happening fast. I mean, look at this timeline. It was just one breakthrough after another. First, you've got Lavoisier in 1789, proving that you can't just create or destroy matter. Total game changer. Then Proust comes along and shows that elements always combine in the same predictable ways. These weren't just random facts. They were like breadcrumbs, little clues leading to a much bigger picture, an atomic blueprint for how reality itself was put together. And John Dalton was about to reveal that blueprint to the world. And that brings us to the star of the show, the atom. Yeah, the ancient Greeks kicked the idea around, but it was John Dalton who gave it real scientific teeth. He said, look, every element is made of its own unique, indivisible little particle. And this wasn't just another theory. This was a whole new way of seeing the world. Suddenly everything, the rocks under our feet, the stars in the sky, even us, was made of the same basic building blocks, just snapped together in different patterns. Then, in 1828, came this, an absolute bombshell. For centuries, people believed in something called vitalism. It's this idea that living things have some kind of special, non-physical spark of life that you just can't find in rocks or dirt. Well, Friedrich Wöhler went into his lab and made urea, an organic compound, something you find in living things, from plain old inorganic chemicals. And just like that, poof, the idea of vitalism was shattered. He proved there was no magic wall between the living and the non-living. It's all just chemistry. So, once we cracked the code of matter, everything changed. It was like we didn't just have the instruction manual for the universe anymore, we had the tools to start editing it. And this new power, it became the engine that fueled the entire Industrial Revolution. Take a look at something like the contact process. It might look complicated, but this is basically a recipe for making massive amounts of sulfuric acid. And why does that matter? Well, this one chemical was absolutely essential for, almost everything. We're talking textiles, fertilizers to feed a booming population, you name it. This was chemistry on a massive, world-changing scale. But at the exact same time all this industrial magic was happening, a really crucial discovery was made. And the crazy part? The scientist who made it was pretty much ignored for more than 100 years. Her name was Eunice Newton-Foote. And her experiment was so simple, yet so brilliant. She just took some glass cylinders, filled them with different gases, and put them in the sun. And she noticed that the one with carbon dioxide got hotter and stayed warmer for longer. And she didn't just stop there. She made the leap. She concluded that an atmosphere with more CO2 would mean a warmer Earth. She figured this out all the way back in 1856. Incredible. And, well, this chart shows you exactly what happened because her work was overlooked. Just look at that graph from 1850 to 1950, and then, boom, that massive spike up to 2020. This is that double-edged sword we were talking about in stark visual form. The very same chemical reactions that built our modern world were also pumping our atmosphere full of heat-trapping gas. And that industrial power really was a double-edged sword. It could create absolute miracles, and it could create terrifying monsters. Let's look at the Haber-Bosch process. This is maybe the perfect example. It's a process that literally pulls nitrogen out of thin air to make ammonia. Now, on one hand, that ammonia becomes fertilizer that feeds billions of people. An absolute miracle, right? But on the other hand, that exact same ammonia was used to mass-produce explosives for World War I. The same process feeds the world and fuels a war. It's a mind-bending paradox. Or how about this one, leaded gasoline? In the 1920s, they figured out that adding a bit of tetraethyl lead to gas made car engines run way smoother. Great! Everyone celebrated. But what we didn't realize was that we were pumping a slow-acting, invisible poison into the air, all over the globe. It took decades for a geochemist named Claire Patterson to prove just how catastrophic the damage really was, especially for kids. 1.2 million. Just let that sink in for a second. That's how many premature deaths are now prevented every single year just because we finally got lead out of gasoline. It's a staggering number. It shows you the insane scale of the damage we did, but it also shows you that chemistry can be used to fix its own mistakes. And this contrast is maybe the most chilling of all. In the 1840s, we discovered anesthetics like ether and chloroform. Suddenly, complex surgery was possible without unimaginable pain. A revolution in medicine, a triumph of compassion. And then, World War I. We weaponized gases like chlorine to cause agonizing pain and death. And later, the Nazis used a pesticide, Zyklon B, for mass murder. It's the same fundamental knowledge, how chemicals affect the human body, used for the ultimate good and for the absolute ultimate evil. Okay, so for our last section, we're going to see how this whole story kind of comes full circle. Remember how we started with the atom as just an idea, a philosophical concept? Well, now it's a reality we can actually see and touch. For most of chemistry's history, atoms were just theoretical. You couldn't see them. It was like trying to figure out what's wrong with a car engine just by listening to the sounds it makes. Chemists were brilliant at it, making all these clever deductions, but they could never actually pop the hood and look inside. Until the 1980s. That's when the atomic force microscope came along and changed absolutely everything. We finally got to lift the hood. For the first time ever, scientists could get actual images with atomic resolution. We weren't just guessing anymore. We were literally seeing the individual atoms, the tiny bonds holding molecules together. The fundamental engine of reality was finally visible. You know, this quote from back in the 1800s is just perfect. Franklin talks about how formulas would add much more precision to our ideas. And that's really what the whole story of chemistry has been about, right? A relentless, centuries-long quest for more and more precision. From a vague idea of 4 elements to mathematical formulas, and now, finally, to being able to actually see the things those formulas describe. So here we are. We've gone from thinking the world was just earth, air, fire, and water to being able to see and build things literally atom by atom. That's an incredible power to have, which means the story of chemistry isn't just about discovery anymore. It's about choice. So the biggest question has changed. It's no longer what is the world made of? It's what should we build next?